I'm gonna remove the word gravity. I'm gonna just remove the word research. Just black hole scanning. Okay, so yeah, you can come back. Let me give you a link. Okay, here you go. Meanwhile, okay, I'm waiting for you to enter. Enter the dragon. Okay, okay, 1 second.
What's the link?
I gave you the link. It's the one with the CQ at the end.
Where's the chat?
It's in the side chat.
Yeah, yeah. Alright.
Okay.
Nice.
Oh my god. Oh my god. Oh my god. Where are you? Well, I hope he got the... Oh, there it is. Okay. Alright. So... The next question is, okay, you want to know, based on this, based on our previous discussion, how do we use this? Okay, this is not entanglement. This is just the wave function collapse. This is the probabilistic...
Yeah, I don't see how we use this to study anything.
Wait, I can't hear you.
I don't see how we use this to study anything.
Okay. So first of all, this I predicted. So I never heard about this experiment from anyone. I predicted this.
I was looking into ChatGPT. It has been confirmed experimentally.
Okay. So just for you to know, I've never heard about. I made this up completely from previous knowledge of quantum physics.
Okay, that's good.
Of actual. This is basically. I think it's just based on understanding. Oh my God, it's reconnecting. I'm sorry, 1 second. So this is just based on just understanding. Once I understood the quantum field theory, that it's basically ether, suddenly I understood a lot of quantum mechanics, like naturally, without anyone explaining it to me. And it makes perfect sense. I mean, not perfect, but relatively perfect sense. So let's forget about this. Let's continue to how do we scan? Okay, let's start from first principles. How do we scan? How would we scan a black hole? So so you create, using some energy, you create, right? So because of Feynman's diagram, it's possible to take a photon and create from a photon, can you create 2 electrons that travel in opposite directions? Can you take a photon and create 2 electrons
Create 2 electrons
out of a photon?
I don't know what you're talking about. Create 2 electrons.
Yeah, right? Because you're allowed to create 2. No, yeah, you're allowed to create 2 electrons out of a photon. No?
Out of a photon? Does it have enough energy for that?
Yeah, let's say it's a very high energy photon. Why can't you convert it into 2 electrons? The only thing that you need to make sure is that you have conservation of momentum. So if this one is spinning if this one is spinning, if this one is spinning up, then this one must be spinning down. That's the only thing you care for. And these are now entangled. These are entangled electrons. The question is, you can ask ChatGPT, how do you create two
Yeah.
entangled electrons? So you just take a high energy beam. I don't know when two electrons will come out of it. I don't know how to do that, but they say that it's. They always talk about they always start this experiment. If you have two entangled electrons, two entangled particles, one is spinning up, the other one must be spinning down because of conservation of angular momentum. You want me to look up what ChatGPT says, how to create?
Yeah, I'm looking that up, but you can too.
Okay, how to create two entangled electrons. Entangled. Okay. Creating two entangled electrons is a process that can be achieved through several different methods in quantum physics. Here are some of the common methods. Spontaneous parametric down conversion, SBDC. This method is primarily used to create entangled photon pairs, but similar techniques can be adapted for electrons. In essence, a high energy photon or another particle interacts with a nonlinear material, I don't know what that is, resulting in the creation of two lower energy particles that are entangled. Okay, look, it's probably just a high energy photon hitting a metal plate, and two electrons are created because of that, just because of spontaneous parametric down conversion. While SPDC is more common for photons, analogous methods for electrons involve using specific materials and interactions that can result in two electrons becoming entangled. It doesn't matter. A quantum dot, okay, direct interaction in a quantum dot. A quantum dot, I mean, let's watch a YouTube video.
No, I mean I get it, but
Right, but let's watch a YouTube video where they do it. Let's see the experiment. So
will we?
I mean, I'm sure there's nothing like it. They for some reason people don't want to show experiments on YouTube. I don't know.
That's
So creating two entangled electrons. How to make entangled. Yeah, but he's not gonna show. Oh, there is the lab. He actually has a lab.
Hi guys, welcome to 20 After Drops. I'm Ben. So this week I want to do just a really quick video, just a follow-up to what we did last week. If you missed it, you can see it here. But we were basically talking about quantum entanglement. Now, quantum entanglement is the idea, just to remind you, that two particles can be linked in such a way that if you go to do something to one, if you go to take a measurement on one, will immediately affect any measurements you take on the other. And this is regardless of the distance these two particles are separated in space. And that is a really weird idea. But what's stranger is the idea that this is always presented to you as a given. That given that you'll have these two entangled particles, but how do you actually produce entanglement? That's what I'm interested in finding out today. How do you actually produce these entangled states? So what I've done is I've come to the Center for Quantum Photonics at the University of Bristol to talk to a man called Jack Carolan, who is trying to build a quantum computer using these entangled states. So it turns out there's a few different ways to produce entanglement, so we'll just be focusing on one. But let's go down to the lab and find out what Jack does and how he actually does it. So Jack, tell me a little bit about how you build your entangled photons.
So we want to get entangled photons, right? And the way we do that is by a process called spontaneous parametric down conversion. Okay, that sounds loads more complicated than it actually is. It's really simple. It's just a process whereby one photon splits into two. So I can show you how we do that over here.
No,
right? So we get,
it doesn't split into. He's gay. It splits into two particles.
we get a big laser beam. We fire it at this.
Okay, yeah, it's good. You start with a big laser beam, so it's a high energy. Okay, it's a high energy photon.
Crystal. It's a special type of nonlinear crystal. When you put light into nonlinear materials, weird things happen. Okay, and in this particular one, two photons pop up. So what the important law is to put light into nonlinear materials.
Hitting,
get a big laser beam.
One second.
We fire it at this crystal. So there's a special type of nonlinear.
So you fire at the crystal. I thought you would fire at a metal plate, but no, you fire at a crystal.
Sounds loads more complicated than it actually is. It's really simple. It's just a process whereby one photon splits into two. So I can show you how we do that over here, right? Because we get a big laser beam. We fire it at this crystal. So there's a special type of nonlinear crystal. When you put light into nonlinear materials, weird things happen. Okay, and in this particular one, 2 photons pop up. So the important laws of physics. Right? Well, there's conservation of energy and there's conservation of momentum. So let's imagine this
Conservation of energy, conservation of momentum.
crystal, this non-linear crystal. I'm going to fire a photon in it, and it's got some frequency. Right? It's got some wavelength, and that tells you about its energy. Okay, so its energy is an h bar over gas. Okay. And then 2 photons are going to pop up.
So it has omega of the particle. It's spinning. So the spin must be the spin. I think omega is the spin, right? What is h omega? What did he say? What is omega? Usually omega
Maybe
is
the angular
spin,
momentum.
but I don't think this is what he means.
So I'm going to fire a photon in it, and it's got some frequency. Right? It's got some wave.
Oh, omega is the frequency. Okay, fine. Okay, so omega is the frequency, meaning just the color of the light, the color of the laser.
And that tells you about its
Okay, that's the photon frequency. That's the color of the color of the laser light. Okay.
energy. Okay, so its energy is an h bar over gas.
Right. So this is just HF equals E according to Planck. Okay.
And then 2 photons are going to pop up. That guy and that guy. Called number 1 and number 2.
So in this case, 2 photons pop out.
Okay. And then 2 photons are going to pop up. That guy and that guy. Called number 1 and number 2. And we know that energy force will equal energy afterwards.
But what?
So the energy of these guys must add up to the energy of this guy. So the frequency of these guys is half the frequency of that one. Okay, so that tells you about
Wow. The frequency is half of each of the W1, omega 1, omega 2 is half of omega P.
the energy of this photon. It tells you what the wavelength is going to be. So we pump it with 400 nanometer light, and the photons that come off are 800 nanometers. Okay.
So you get a laser beam that is of a different color. Wow.
It's instead of beam of light, it's just nonlinear crystal, and each photon that comes in then produces 2 photons coming out of it.
Not each one, some of them. There's a very small probability it's going to happen. But because we've got a big laser that's got trillions of photons in it, you can make that probability appreciable. So we see lots of photons. Conservation of momentum, right? That's also very important. So if you look around here, right, our input photon is moving that way. Okay, so what we don't want to have is 2 photons coming off here. That's really bad. That physics doesn't like that. So that's actually why we've got 2 prisms bouncing light off here. The photons come off like that.
So at this point, we've made our 2 photons by sending in this light into this crystal. Is this entanglement? Have we done it?
Not quite yet. It's not quite the useful entanglement that we need to do something like build a quantum computer, okay? Because to understand how you do that, you really need to know something a little bit more about this crystal, just a little bit. And the crystals pair.
Oh, so you can use this to build a computer. How will you use this to build a computer? I mean, the computer can work really fast. I mean, you can, first of all, you can use entanglement for instant communication. I mean, you could definitely break the speed of light with no issue of communication. I don't see the problem. So we're no longer limited by the speed of light if we believe in entanglement.
About polarization, okay? They care about the way the light moves inside it, all right? So if imagine they get a crystal. If I input horizontal light, for H, the photons that come out are going to be vertically polarized. So this is one type of crystal. Okay, I'm going to call this number 1.
What kind?
If I input horizontal light for H.
Okay, so how do you input horizontal light? You just put a filter. You just put a filter that only has horizontal slits.
The photons that come out.
But I mean, the way light travels, right? Because the waves, right? You need to actually imagine the three-dimensional sphere. The three-dimensional sphere internally, right? The way they draw it, the electric field in the electromagnetic field, they always draw the electric field going up and down, right? Are you there?
Yeah.
So the way they draw in Maxwell's, when they show you the interpretation of Maxwell's equations and they show the electromagnetic wave, they're always showing the electric field going up and down, right? And the magnetic field going right and left.
Yeah, but that's like just mathematics.
it's not
That's
just
really-
mathematics.
Yeah,
I mean,
it
it's,
is.
no, it's an actual. There's an actual physical wave. What do you mean? You're right now. There's light reaching your eye. Now this light has a direction. So they when they draw it up and down, that's a specific wave that's caused by an electron that moved up and down. So an electron that moves, let me draw this. I mean, they don't teach this. I don't know. I mean, they expect you to figure everything out on your own. Or maybe they don't know it themselves.
In a way, this is like usually they model it as like a spiral.
No, the spiral is something completely different. There's nothing to do with this. The spiral is with the eye and the Schrodinger equation. I'm not talking about Schrodinger right now. Schrodinger is the probability of creating a particle out of the wave. Where will this? What is the probability of finding the particle at any place? What is the what is the probability of finding the particle, of measuring the particle at any location? That is Schrodinger's equation. And then they usually use a spiral. But the way Maxwell's electromagnetic field works is you have an electron or an electric whatever, like an antenna. You have an antenna. How do you create a signal? So you charge it full of electrons, and then you discharge it, and then you charge it and discharge it. And basically, you're pushing electrons up, and then you're pulling them down. Or maybe what they do sometimes is they have this two steel balls connected with a wire, and then they charge it like with negative electricity until they get a spark, and again,
Yeah,
and they get a spark. So you can create a spark at an interval. Every spark, you're causing electrons to jump from one ball to the other. Is this all negative, or is it negative and positive? Wait, a spark?
Yeah, but it could be both. But but that's like an impulse thing. That's different.
But this is the picture they show every time they discuss Hertz discovering electromagnetic waves.
Yeah, I mean they show the picture, but like for
Anyway,
example, antenna engineers don't even really use that. Like what
what engine?
antenna engineers use Euler's formula. They don't use Maxwell's.
Antenna engineers use what formula?
Euler's.
Euler? I don't know Euler.
Euler, the
Anyway,
mathematician.
yeah, no, I mean I don't know Euler's formula. Anyway, look.
You do know Euler's formula. It's the one with the exponential thing for sinusoidal waves.
Oh, that's Euler. Okay. Anyway, so you basically you somehow cause an electric charge to go up and down. Now this going up and down translates literally to an electric field going up and down. You're shaking up the ether. You're pulling up the fabric of the ether and then down in terms of the electric field. You're causing an electric disturbance. So when you pull an electric charge up, right, so you can imagine a positive charge here that is being dragged up. You're pulling up all these positive charges, and this progresses that way. But this is just a side view. From a top view, yeah, I think I know. Okay.
Mm-hmm.
So this
I'm
is
here.
what?
I'm here. If that's okay, you stop.
No, no, I ran out of room, so I'm gonna create a new one. Yeah?
Ran out of what?
I ran out of room to draw my drawing.
Oh,
So,
but I'm not seeing your drawing. I'm seeing your hands.
oh, I'm not sharing it. Oh my
Yeah.
god, why are you not telling me that I'm not sharing?
I thought you were talking about the drawing on on the video.
The drawing on the video. Oh my
Yeah, he was drawing.
god.
He had a
Oh my
drawing waves there
god.
too.
Oh my god. I cannot believe it. This happens to me so often and I'm tired of it. I'm so tired of doing this to myself. Anyway, let's start again. So let's say I have an antenna and I'm gonna push in electrons and then I'm gonna pull them out. Push in electrons, like charge it with electrons. It's basically a capacitor. You're charging it with electrons and then discharging it. Charging it with electrons, discharging it. So when you charge it with electrons, let's say, right, you're creating a disturbance, a disturbance in the electric field. So you can imagine an electron here that as you're charging this antenna, this electron wants to run away. When you're charging it with electrons, when you're charging the antenna with electrons, you're causing all the electrons to run away from the antenna, just like a sound wave.
Yes, that
This
one
is-
don't actually run away. That's not really what happens, but
What do you mean?
yeah.
This is electric repulsion. There's an electron here, so they want to move away. What do you mean? So if the antenna is in the middle of the room, so some of the charges will move to the right and some of the charges will move to the left. Right? You're gonna have when you charge up the antenna with a negative voltage, negative potential. You're going to cause a disturbance in the electric field. You're going to cause these guys to move away.
Yeah, the electrons don't really move away. It's not exactly what happens.
Yeah, you're right. That's not gonna create an electromagnetic wave.
No, it happens here is that you get radiation basically.
Yeah, I mean,
You
really,
get
what
an
I want to do.
electromagnetic wave, but
Let's-
it's not.
let's
It's
imagine-
not made of electrons.
Let's imagine something simpler.
You
Let's
get
take
something like a radio wave.
let's take an
But no,
elect.
it works fine with radio waves. Like you're
Let me ask you this: if I take an electrically charged, a negatively electrically charged piece of metal, and I just move it up and down, is this right? I'm going to be able to notice it. Let's say I have a test electron here, right? It's going to feel it because right here it's being pushed this way, and when the electric charge reaches this point, the electron is going to feel a oh my god, it reset. The electron is going to feel a push this way, right? So the electron is going to feel it. So basically what you're getting is you're getting an electric disturbance. Let's just talk about the electric disturbance. Okay. But right, so this electron is basically, sometimes it feels a push this way, sometimes this way, and sometimes this way. So sometimes sometimes it wants to because what I was thinking is sometimes it wants to move up and sometimes it wants to move down. Right? That is an how do you create an electromagnetic wave? But the electromagnetic wave, ultimately, a test particle needs to want to go up and down. And that's what we see in the diagrams of the electric field and the
Yeah, I get it.
and the magnetic field. Yeah,
was,
it's
was not the best choice of direction.
and the, and
Should have
no,
done it
let's
opposite.
let's do it this way. So oh, it has to start from here. I started from the wrong place.
Yeah. But see, they don't necessarily need to be out of phase there.
No, they're in
Like that.
phase. I think they're in phase.
No,
So-
they don't. Okay, in phase or whatever, but they don't necessarily need to be with that phase. They usually
No, but they're at no, but
in
they're
Euler's
at
formula. They're like they're like the wave, the electric wave is zero when the other one is maximum, and vice versa. And that's the
no,
one that's used by engineers
but
because
usually
that one maintains constant power. But it's okay, whatever.
But that's-
It's not.
but that's not possible because an
That's definitely possible. That's like experimentally verified. for,
Wait,
like, with
wait,
like millions of things, billions of instances.
okay, so Maxwell's four equations, they say that, I mean, they're just a summary of experiments, so we know that an
More or less.
electric,
I mean,
a ch-
you have to understand that Maxwell's equations were altered and all of that. So
right, but
I'll
the
have to
experiment,
check the original ones. Because
Wait.
Maxwell's equations don't really include phase.
wait, of course they do.
No, they don't. Where's phase in Maxwell's equations?
What do you mean?
Yeah, where's
Look.
phase in Maxwell's equations?
Okay,
That's
hold
what I
on,
need.
hold on. Look, if you move, right, change in electric field causes a magnetic field. Change in a magnetic field causes an electric field, right?
Okay. So,
So you're saying that they have to be? Oh, that means they're completely out of phase.
here basically, yeah.
Because at this point there's no change. This is
Yeah.
the zero change in the electric field, so it has to be. So the other one has to be zero. So the magnetic must be zero because there's no change. Okay, so you're right. So this is incorrect. Okay. So if this is the electric field going up and down, which means a test particle here is moving up. And a test particle here is moving down physically. This is X. This is voltage. How do you say time? You can't even discuss time. Yeah, you cannot discuss. You can just say that this is of a wave of a certain frequency. Anyway, and this is Y. So Y is the magnetic field. So change, there's no change of electric field here. This is maximum change. So this is where it's zero.
Wait. But like a change in the magnetic field produces the electric field. It doesn't produce change in the electric field.
Wait, change in electric produces magnetic. Change in magnetic produces
No,
electric.
change in the magnetic produces electric.
And
Right.
change in electric produces magnetic.
So the maximum change in magnetic
Yes,
needs
yes.
to produce electric. So it needs to be
Fine.
it needs to be as I said.
So-
Okay, fine.
So they're completely out of phase. Okay, so
Yeah.
maximum voltage is right. The first derivative is zero.
Yeah.
So V prime is zero. V prime is zero. That means that B is zero. I mean, the first derivative of this one is
Yeah.
B, is the magnetic. Okay. So the magnetic must be 0 here and must be maximum here.
There. Yeah, that's
Maxi-
the always.
Okay, so it's maximum here and then it's minimum here.
Yeah, I
And
don't
then-
know why they use the other representation always.
It's
Never
wrong. They
really-
shouldn't. They
I
should stop
never really
it.
got that. Why is is there any reason for that?
I don't know. So this is my drawing is so bad that it's difficult to know what's going
No,
on.
it's understandable.
No, I want to add now the magnetic. Oh my god, my hand hurts so much.
You wanna go to sleep?
No, I need to go to sleep. Yeah. Oh, it's very late for me. You need to you're working tomorrow?
Yeah, but it's okay. I can like maybe half an hour more. But no, more
No,
than
no,
that.
I'm not gonna stay for another hour. No way.
Half an
Okay.
hour.
No, yeah, less. Let's do a couple more minutes. Let's
Okay.
just finish this discussion. Anyway, so
Yeah, I think we
um,
finished this discussion. Like,
Yeah, this discussion
yeah,
is
we were
finished.
in
So,
agreement.
yeah, so but what I'm trying to say, this motion up and down is basically created by the antenna voltage going up and down. Or you can imagine like when you look at sunlight, right? The sun has many electrons and they're shaking in every which direction. So some of the electrons in the sun, there is an electron that's shaking during a certain instant up and down, and it's causing an up and down wave, but this is just a cross section. Don't forget that what's coming out is a spherical wave. So first of all, it's not a linear wave. It's let's go to one more dimension. This is, I mean, I don't understand why I'm
Yes,
the only
that's-
one who no one explains it. People only show the cross section of a single dimension. Ridiculous.
Yeah.
Okay,
definitely.
so
Right,
this is
yeah.
3D Maxwell.
The thing is, you have to imagine this in 3D. If you
Yeah,
imagine this in
it's-
3D, it's going to be like like spirals.
No, there's no spiral.
It's going to be
No,
like spirals.
no, there's no spiral. No. Anyway, so basically you have an electron in the sun right now that's jiggling instantaneously up and down. And it's creating a 3D, right? It's creating a 3D expansion, right? So if you do this, so this is a wave, right? It's a 3D expansion. This is a top view. So this is a side view. This is the top view. But even that's not enough. It's three-dimensional. It's a three-dimensional object, and it's actually it's almost a sphere. It's not really a sphere. It's almost a sphere. But you could view it as a sphere. I mean, it really depends. You really need to use Maxwell's equations to create a three-dimensional field vector functioning diagram, meaning an actual a moving vector diagram. No one has done this. Someone must have done this. Anyway, so but the point is, what I'm trying to say is that this is just one electron in the sun. Another electron is going this way. Another one is going this way. Another one is going this way. Another one is going. So the sun is composed of many of these waves going every which way. But the one going up and down, we can filter those using a comb-like object that simply has thin slits that are vertical. So you can have sunglasses that just have thin vertical slits. So it's filtering just the waves that are moving up and down. Just those waves, they are still three-dimensional, but this is just a certain direction, and that's what he's showing here. So here it's showing an electron in the sun that was moving sideways, or in the laser emitter. There's also all these waves going every which way, even though, so the laser is light amplitude amplification with using resonance. Using resonance, they're causing all the waves to be identical in a certain direction. Anyway, let's see what he says.
And the crystals care about polarization. Okay.
So that's called polarization, the direction. The crystal, obviously it's crystal, so it has a direction. So there is the crystal has a preferred direction. So it's going to filter out all the other directions except for one.
They care about the way the light moves inside it, alright? So if imagine I get a crystal. If I input horizontal light, the H, the photons that come out are going to be vertically polarized.
Wait, how is that?
So this is one type of
That's
crystal.
because of
And we'll
the
call this number one.
What?
I mean, how the crystal works.
But how? I mean, a crystal, it's just crystal. Just because of the structure of the atoms, it filters out. So, this, I don't know
Yeah,
if
it can
this is
change
correct.
the direction.
How? That doesn't make any sense. That doesn't make any sense.
Because
No, I think he's wrong. I think incoming is any direction, and what comes out is one direction.
that could be.
I don't think this is correct.
What I can also do is rotate this guy by 90 degrees. Okay, just do the same one, rotate it by 90 degrees, such that if I input vertical light, okay, the photons that come off will be horizontally polarized.
No,
You get
this
one
is
of these.
incorrect. He doesn't. In my intuition, he's incorrect. So what's going on is that unfiltered, unpolarized light is incoming, and based on the way he is directing the crystal, he's getting polarized light coming out. Because he's filtering. This is not horizontal. This is not vertical. This is just unpolarized light incoming. It's unpolarized as far as I'm concerned, and you're getting polarized, and by rotating the crystal you're filtering a certain direction. By
Yeah,
rotating
but
the
isn't
crystal.
talking about polarization, really.
Well, yes, of course he says polarized. Yeah, he's talking about
It
polarized.
does?
Yeah.
So this
Okay.
is the H, the way the light moves inside it, alright? So if imagine I get a crystal. If I input
Right.
horizontal light, the H, the photons that come
Horizontal
outside
is
it, right?
polarized.
It feels a quantum confuser, okay? Because to understand how you do that, you really need to know something a little bit more about this crystal, just a little bit. And the crystals care about polarization, okay? They care about
You see, the
yeah,
crystals
it's
care
polarization,
about
yeah.
polarization.
the way the light moves inside it, alright? So if imagine I get a crystal. If I input horizontal
Which makes sense. This makes physical sense. I mean, that is the nature
Yeah.
of a crystal. It has a preferred direction. That is the definition of a crystal.
light, the H,
That's incorrect. That doesn't make any sense. That you can convert horizontal to vertical light. That doesn't make any sense. You cannot do that.
Yeah, that
photons
doesn't
come out.
make sense, actually. You're right.
to be vertically polarized.
I mean, that goes literally
And can
against
you
everything.
invert? Maybe there's some crystals that can actually invert polarization.
How? How? You need. It's a three-dimensional wave. How do you just? How? I don't see how. Unless it interacts with the actual, unless it causes a vibration inside the crystal. You think it's actually causing a vibration inside the crystal?
Yeah, it's causing electrons to vibrate inside the crystal.
But why
and
would
then,
they change direction?
like,
Okay, whatever.
depending
Maybe.
on the structure of
We'll-
the crystal.
Sure, we'll look into it. It's not critical.
Yeah.
So this is one type of crystal. Okay, I'm going to call this number one. What I can also do is rotate this guy by 90 degrees. Okay, just do the same one, rotate it by 90 degrees, such that if I input
So he called that number one. He doesn't mean it's number one crystal. It means it's unrotated. Number one is rotation one. Number two is rotation two.
vertical light, okay, the photons that come off will be horizontally polarized. You get one of these and one of these, put them up next to each other, okay? Crystal 1, crystal 2, and you input what we call diagonal light. Okay? Diagonal is a mixture of horizontal and vertical. And if you get photons come out, you don't know whether they were created in the first crystal or the second crystal. Okay? So you've got to say it's either horizontal or vertical. Okay? And that is an entangled state.
I have no idea what he's talking about. That is what? I don't know what he's talking about.
Okay, put it back a little bit.
No,
Got a
forget it.
little bit
I don't
closer.
like it. Look, I want him to create 2 electrons. I'm not asking for much. They always talk about 2 electrons that have opposite spins. So let's look for creating 2 entangled. I asked for an electrons. So let's do the search again. This is no good. How to make entangled photons. We should have noticed this and we should have rejected this. Okay, second one, creating entangled photons. Quantum entanglement
It will be the
explained.
same.
What?
It will be basically the same.
I don't understand what you're saying.
It will be basically the same. Won't be very
No.
different.
No. I want to see how they create Classroom 8, quantum entangled electrons.
We'll start out with 2 electrons that have been. Here's a water wave. It's described by a wave function that determines its operation and a wave equation that determines the change in the function over time. We can channel this wave into 2 directions, say A and B. With enough time, we can create a great distance between the 2 branches. If we examine branch A at some time t and find that the wave is at a peak, we will know immediately that at that exact time, the branch B wave will also be at a peak. We don't ask how did the A branch inform the B branch that it needed to be at a peak. We did not analyze whether information was flowing from A to B faster than the speed of light.
This looks like
We simply note
against
that
quantum
both
entanglement.
branches are a part of a single wave equation.
Wait,
What
what are you saying?
This looks like to be against quantum entanglement.
Yeah, he's going against, but I don't
Yeah,
think so. He has
But
the
let's see.
way-
Let's see it.
Yeah, let's see.
that determines its state at any time t. Of course, if we drop channel A's water off a cliff, the wave in channel B will continue on its merry way. To help isolate the key differences between classical mechanics and quantum mechanics, let's look at one more classical example. Here we start with 2 coins, each with the heads on one side and the tails on the other. If we put them both into a spin and send them up the 2 channels, we note that during the journey, they exhibit neither heads nor tails. But they carry a probability that, once stopped, they will either come up heads or tails. The probability is 50-50. But unlike the water wave, the results for one of them does not tell us anything about the results of the other. They are independent.
It depends,
But like water
it
waves,
can.
the outcomes can be predicted if
No, I wouldn't say that. I would say that if you mechanically
It's a
spin
bad
them,
example.
and you
like a
maintain
horrible example.
angular momentum, then you should be able to predict one from the
It's
other.
like if you divide a coin into.
But also, how do you stop them
two.
instantaneously? How do you do that? Like that doesn't. That's
And
like.
if
crazy.
you stop them exactly at the same
How do you
time.
How do you stop them exactly at the same time?
Yeah, you get, but it's like.
Forget it. Let's continue.
abstract.
starting conditions and channel environment are known. For the quantum mechanics view, we'll start out with 2 electrons that have been put together to entangle them. Entangled particles are particles that have their quantum states described by a single wave function.
Okay, that's useless. Goodbye. I thought he was actually.
Quantum
gonna,
mechanics has looked
He was going to discuss an experiment.
In a go-
Alright, quantum.
This is an introduction to the TU Delft undergraduate lab on quantum entanglement. We present and explain the experimental setup you will use to test Bell's inequality and observe polarization entanglement with pairs of photons.
Okay,
In
that's the
19
same problem. It's photons.
my chem.
After the embarrassing failure of our hoax, you know, the one where we tried to fool people into thinking our brains were quantum entangled, George and I needed to get out of town. So So we decided to drive upstate to a physics lab where they observe what else? Quantum entanglement. If we could see entanglement firsthand, perhaps our next hoax would be a bit more convincing. Our destination? The lab of Enrique Galvez, physics professor at Colgate University. Enrique has built a machine for his students to observe quantum entanglement directly. The apparatus may look complex at first,
Yeah, it looks like photons again.
but don't worry, we'll break it down for you. It all starts with laser light.
Yeah, it's photons.
Yeah. But I mean, the principles are the same.
See, when they talk about it, they talk about electrons. They never talk about photons.
How?
Photons.
In this video series, we will learn about what an atom is and what atoms are made of.
Anyway,
After the
there is no quantum entanglement of electrons on YouTube.
modern physics.
Scientists and their never-ending.
Entanglement can happen through natural processes. For instance, if you take an atom, typically one uses, say, an atom of calcium, and if the atom is excited so that it has more energy than it would in its most quiescent state, then as it sheds that energy, it can, for instance, emit two particles, two photons, back to back. And the two photons streaming away back to back can be in the entangled state. So they definitely both emerged from a common origin, but that doesn't make it any more understandable that what you do to one over here can affect the other over there.
Okay, I mean, using the same principle, you should be able to get two electrons. Okay, polarization, same problem. Real-time imaging of quantum entanglement.
I've made a video.
Let's see, okay, let's just put experiment. There's no experiment? Experiment, and I gotta go to sleep. Because I have to wake up early tomorrow. No, there's no, there are no experiments on YouTube.
I want to be showing you.
No, these are all the same. Photonic entanglement. Bye. Oh, entanglement explained and debunked.
Extreme Finitism presents Entanglement and Bell Test Experiments, a local hidden variable solution.
That, I mean,
Extreme.
I don't know
Let's see
Bell's,
that. Let's see
do
that.
you know?
Wait,
No,
what's the
I don't
title
know
of the
Bell's.
video?
I don't know Bell's theorem. No, we need to go back to, let me just
No,
show you.
but tell me the title so I can go.
I'll give you this one.
Wait.
I'll give you the
Yeah,
link.
quantum entanglement explained.
Copy
Okay, give me the
link. I'll give you the link. I'll put it in the Discord.
Yeah.
Okay, not spooky after all. Yeah, we should watch it maybe next time. But let's get back to how we find out, how can we scan a black hole. Anyway, you somehow, I don't know how, you create two entangled electrons. One spin up and one spin down.
Just ask ChatGPT. Like ChatGPT will tell you.
What?
You haven't. Where did you put the video?
In the chat, in the side chat of Discord.
Oh,
In
but
the-
I'm not there. Okay, I'll
Oh,
have
you're
to
not there.
open-
You don't have to go. Okay, I'll put it. Let me put it.
Wait.
I'll put it here too. I'll put it.
Yeah.
No, you don't. Here, I'll put it here too. Wait, who is Dream Rother? Now, can you talk to me? Well, you can. Oh, they cannot join us.
No idea.
This is. Oh, it's a long time ago.
Tell him to join Discord.
Okay. Okay, so I'm on Discord. I'm on Discord. So how do you scan a black hole? So you can create. We saw that you can create two entangled electrons, right? One spin up, one spin down, right? So far, so good.
Yeah.
Okay. So then you throw one of them into a black hole. So this is a black hole. So you take this one and you throw it into the black hole. So far, so good. Okay. The next step is to take this guy and measure it, right? You don't know.
Okay, so the problem here, quantum entanglement will be broken if you do that,
Why?
because it's very fragile.
When it's very fragile, I mean,
And it's like to get like a symmetric result, you'd have to make the same operation that you made in the black hole.
I cannot hear you. What?
And in order to get the result, the same result, you would need to make the same operation that you made in the black hole.
But
So
look, you don't
you
know.
can't really get any information from that. No.
Wait, you don't know anything that's going on inside the black hole. You can have a theory what's going on inside the black hole.
Yeah, that's why you can study it like that.
Okay. So, what did you just say?
That's why you can study it like that.
That's why you can or cannot?
Cannot.
Okay, I don't know what you mean. I didn't explain it yet. So, I'm assuming that this is a clean environment. So, the black hole, you know, it's very clean. It's a pristine environment. There's just an empty black hole. It's very clean. And you throw in one electron into the black hole. It disappears into the horizon, into the black hole. Now you take the other. Now you do this, of course, many billions of times per second. So basically, you're getting you have some photon ray, and you're getting a beam of electrons this way and a beam of electrons this way. So there's two beams. And this beam goes into the black hole, and this beam goes into a detector. And you measure the spin. Now, when you create this, and I'm saying that it's spinning up and this is spinning down, I actually don't know which way they're spinning. They're both spinning opposite
Okay,
of
but
each
the
other.
measurement needs to be symmetrical. So
Wait 1 second. So I don't know which direction it's pointing when it's being created. So you should be getting any which direction. You're getting electrons of every whichever
yeah, but the problem is the measurement needs to be symmetrical. So
What do you mean?
like if you measure, you have to make the same measurement
No,
on both sides.
But I don't know what, right? As soon as I'm assuming, let's say I have a theory what happens when this is thrown in. I'm assuming as soon as it crosses
Okay.
the event.
I
What?
see, but still I don't. Okay, continue.
Okay. So I'm assuming that, right, we have a theory. We happen to have a theory, right? We're following Bacon's scientific algorithm. So we have a theory what exactly is behind the event horizon. We want to test that. So we know that there is basically a neutron star inside the black hole. So the question is, what do we expect this beam to do when it impacts, right? It's going to vary. As soon as it crosses this boundary, basically right after that, it's going to explode. It's going to blow up. It's going to hit these neutrons. This neutron star. It's just going to crash against this neutron star.
Okay, you still there?
Yeah. The question is, does the neutron star have any is it like a magnet? So we can assume, okay, so we can assume that internally a neutron star is spinning. So this is a spinning black hole. So we know that, right, all black holes are spinning, and because they're spinning, they have a magnetic field. So this magnetic field has a very clear direction, a clear magnetic preference. So it's basically a Stern-Gerlach detector.
Yeah, but still, you need to make the same measurement that you make. You need to know the measurement in the black hole.
All you need,
I mean, yeah, you could say like, okay, so the black hole is going to measure it this way, so therefore if I measure it this way, but like you could get one spin or the other because you don't know. Still doesn't work.
No, but you have a theory, and based on the theory, you're making a prediction.
Yeah, but what's your theory?
I don't know. I'm trying. I didn't. This is the first time I'm going through this. I don't know yet.
Okay, but still, I don't think this is going to work. Because like you don't know what the spin of the electron is beforehand, so you could just get just about anything.
No, but this is exactly the Stern-Gerlach experiment. There's no reason I should not be able to figure it out.
How'd you figure it out?
I don't know. Let me think. You're not letting me think through this, so I can't have an answer if you don't let me think.
Okay.
Okay, so you're throwing in the electron, and let's think about the field here. So let's assume internally it's spinning horizontally. So that when the electron comes here, we need it to interact and be absorbed, right? It's going to be absorbed. It's going to be absorbed by the neutron star. This absorption is going to collapse the wave, right? Because this beam is really, it's invisible. And because it's invisible, really, it's a wave. So it's a wave of electrons. Each electron is waving through the ether, but it still has a spin. Let's say it's an upspin. So if it's upspin, and this is rotating like this, so there's a gradient, so it's going through a magnetic gradient. So, I mean, we would have to think what is this electron beam always going to experience, right? Because this is the conditions inside are not changing, therefore whatever the magnetic field causes the electron, let's say, right, it causes the electron for half of them to go up and for half of them to go down, right? Some of them will go exactly up and some of them will go exactly down, just like in the Stern-Gerlach experiment.
Okay, yeah, that's true.
But we can calculate when this will happen. Based on the size of the event horizon, we can calculate the size of the neutron star behind the event horizon.
Alright, but still.
Wait. So we know at what time they will interact. They'll go up and down. Some of them will go up, some of them will go down based on their random spin. Okay. So based on this, you expect this beam to also, if you put it through the Stern-Gerlach, you also expect 50% to go up and 50% to go down. And that's the prediction. that can only be true if everything we said is true.
No, it could be true in other ways. And you still have the same problem. Entanglement measurements are only valid if they're symmetrical.
One second. So
So the fact, okay,
No,
so
let-
you
let's-
would get
let's-
like you just get like random directions and you'd see if they always go 50-50, right? Like that's what you're
okay, so
proposing.
that's not a good That's not a good setup. So we
No,
need
no,
to.
but there's one way. You'd see if they all go in the same direction or if they all go 50-50. Because using more electrons, you can tell something.
I
Now,
cannot
that's interesting.
understand what you're saying. You're like.
Okay,
You're
it's
saying
interesting because if we do it with a lot of electrons in this way, we could technically find some direction, like assuming there would be one direction, where you'd get like where you'd get like this 50-50 behavior. But
Let's
still,
talk about let's talk about a single electron. So if every time you
with a
fire
single electron, you can tell anything.
one second. So let's say you fire a single electron and it goes this way and the other electron goes this way.
Okay.
But let's say you delay, this is a delayed, you delay this. You somehow delay this through, like, this is a longer distance. So this is going to happen first, and this will happen second. So you fire one photon, and then this electron gets thrown into here and either goes up or down. Now the other electron, so it's entangled. So once this was measured up and down, but you don't know which. So you
Okay.
cannot get the information out. I mean, the information comes out because, let's say, because this is up, this must be down. Wait a minute. If this is up, but you don't know if this is up. You don't know if this is up or down, so it could
Yeah,
go
that's the
either way.
problem. That's why with one you can't do anything.
No,
With many,
no,
however,
no,
it's
no, no,
much
no,
more
no,
interesting.
no, no, no. So this is either up or down. This means that if you measure this up and down, you'll get 50-50. But if you change the angle, of this apparatus, you no longer are you going to get 50-50.
Okay, but
Right,
for
because-
that you need multiple electrons.
No, a single. Wait, no, it's not
No,
gonna
you
help.
need multiple ones.
No, wait. I don't think it's gonna help you. Look, once this was tested up and down, but you don't know which, and you don't know the result. I don't think you can use it. Wait.
Yeah, that's why you need multiple electrons, but you're still assuming that the spin isn't changed in any way.
I don't understand what you're saying. I'm still
You
assuming
still
that
you need multiple electrons, and you're assuming that the spin isn't changed.
I'm assuming the spin isn't change.
Yeah.
What do you mean isn't change? Isn't changed?
Well, that the spin. Okay, no, that's okay.
Okay, I'm assuming the black hole is spinning, and I'm actually, because of 1 and 2 is my timing, so I know when to expect it. At least I know when the wave collapses. I know when this electron is absorbed. At least I'm predicting.
Okay, if you
question
can
is-
know when the electron is
I
absorbed.
mean, as soon as this electron collapses, as soon as this wave collapses into a particle, only then will something happen to this experiment. I mean, it must have an influence. Whatever I do to this one, does it not have an influence on the behavior of this experiment? There's one
Okay, so
experiment.
that experiment is like measuring multiple directions, right?
I don't understand what you're saying. That
That experiment is measuring multiple directions.
that which
Yeah,
the
that's
black
the
hole.
experiment we're having right now.
I mean,
We're measuring various directions.
look, I'm assuming the black hole is spinning in a certain way. So will that have any effect on number 2? Will number 2 be influenced by the direction of number 1 or by the timing of number 1? Because I cannot get the information if it went up or down. I don't know. But at least I know that it was tested, it collapsed at 1. And I know the direction that it was tested. I know the angle of the Stern-Gerlach of the black hole. The black hole is a Stern-Gerlach experiment. The question is, if I have two Stern-Gerlach experiments, can I tell something from the result of one by the results of the other? Two Stern-Gerlach. So let's ask ChatGPT. That's really the question. So ChatGPT, can I predict the Stern-Gerlach experiment result of Can I predict the result of one electron? No, I need to set it up. So given two Stern-Gerlach experiments. Okay, that's given. One electron goes into one of the two Stern-Gerlach experiments. The other electron then goes into the other Stern-Gerlach experiment. Okay, we know the angle. Let's say both angles are the same. No, we know. Oh my God! Do you think ChatGPT is going to be able to figure this out?
Yeah, you might.
We know that in the first Stern-Gerlach experiment, we know the angle. It's measuring up in the experiment. The electron is measured vertically. That we know. We also know when it's measured. But we don't know the result. Okay. We can run the second Gerlach experiment after the first was run. Can we get any information from the first Gerlach? No, not any information. Can we know anything about the up and down? How is that going to help us? No, I'm not looking for the up and down. What I'm looking to see is will my experiment change as I rotate, as I change the direction of the Stern-Gerlach experiment, the what do you call that? The position, the angle. As I change the angle, so as I change, so as I change the angle of measurement of the second Stern-Gerlach experiment, as I change the angle, will I get results that are correlated to the first Stern-Gerlach? I honestly doubt. I don't think. Okay, the scenario you've described involves two entangled electrons being measured in two separate Stern-Gerlach experiments, where the first experiment measures the spin of one electron in the vertical z-axis direction, and the second experiment measures the spin of the other electron at an adjustable. Oh my God! It understands. It actually understands
Yeah, it
the
understands
setup.
really well.
Correlation between measurements entangled electrons. If the electrons are entangled, their spin states are strongly correlated. For example, if the electrons are in a singlet state where their total spin is 0, the spin of one electron is opposite. Okay, that's a given. First measurement vertical. When the first electron is measured along the z-axis, the wave function of the entangled pair collapses, and the second electron's spin state becomes defined relative to the first. However, you don't know the result of the first measurement, only that it has been performed, and I know the angle. Okay, but ChatGPT knows that I know the angle. Okay, second measurement, arbitrary angle. When you measure the second electron at an angle theta relative to the z, the probability of finding the electron in either spin up or down will depend on the angle theta. Really, expected result, correlated outcomes. The outcomes of the second Stern-Gerlach experiment will be correlated with the result of the first experiment, but the strength of this correlation depends on the angle theta between the measurement directions. Quantum correlation form. So according to this, we should be able to scan the black hole. The probability of the second electron having a spin up result relative to its measurement axis is given by cosine theta over 2. Exactly. And the probability of spin down is sine whatever. Okay, it's just the complete. This means that that as you vary theta, the correlation between the results of the two measurements changes. Okay, look. Because when you measured the first electron, you caused the other electrons' direction to change. The spin changed, either up or down. That's exactly the point. You don't know if it changed to up or down, but it became vertical. Until then, it was not vertical. So we can go back to the previous note. So as soon as number 1 took place, number 2 became vertical, up or down. But it became vertical, so that only vertical would have been 50-50. Every other direction is less than 50-50. And that's the answer. So yes, you can definitely measure, you can scan a black hole with you don't need to fire a single electron. You can fire a beam. It's not gonna make a difference. You can fire a beam and you'll see it. You'll definitely
you have
see
to
it.
fire a beam.
No, you don't have to. You can fire a single. It doesn't matter. But how does that work? Now the question is, how does it work? This, right? Because we think through the. I think.
But you
through
have
the
to make
ether.
sure. But the problem here, wait. The problem here is you have to make sure that The electron spin. Wait.
I can't hear
Maybe
you.
not. Maybe you don't have to make much of anything.
No.
I'm thinking.
According to
Okay,
no,
so the
thi-
electron spin can be up or down. Yeah, you just have
Okay.
to find the direction. Yes, that works.
Yeah. So, so this is, in my opinion. So, okay. So I already thought about this the other day when I texted you. I didn't think through the details, but I texted you. It's doable.
Well, your stream is kind of. I'm losing
No
you, I
good.
guess.
Wait, what?
Right?
You
I'm
cannot
losing
hear
you.
me? You're losing me?
Yeah, I'm hearing a lot of latency.
Okay. I mean,
No,
maybe.
it's fine. It's fine now.
Yeah, I saw my radar going down. Now it's going up. So, as it says here, we
Okay.
should be able to use entanglement to scan the internals of a black hole.
Yeah,
So,
you would be able to.
And this was my intuition. This is on the 17th. Oh my God, you're not gonna believe.
Again, provided that entanglement is a real thing.
No, no. And look, provided that, I mean, this is just the double slit experiment.
Sweet.
So if you believe the double slit experiment was conducted on electrons successfully, that shooting an electron beam through a double slit created a wave pattern. That's all you. If you believe that, then you should be able to scan a black hole, because this is based just on particle wave duality. I think. I'm not using
Yeah, it
anything
is.
else. Right. So how does this work? What are my assumptions? Why do I believe this? So, in the particle wave duality, every time we see a single electron showing up, we fire an electron, it goes through the two slits as a wave, it interferes with itself, and then collapses on the detector as a particle. So how does it know to return into a single particle? How does it know to collapse to one spot? How does it know that? It's a wave. How does a wave become a single particle in the universe? That collapse is that's the same mechanism of entanglement. And in order to have preservation of energy and preservation of momentum, but preservation of energy, just preservation of energy. Conservation of energy. Just in order for the universe, because we see the universe does not blow up, that means we have conservation of energy. If you have conservation of energy, that means the double slit experiment. The double slit experiment proves conservation of energy. Right? But the double slit, let's think about the double. What does the double slit experiment say? Okay. Double slit. So the double slit says that you fire a single electron or a beam, it doesn't matter. You fire a beam of electrons, it goes through the two slits and you get a wave pattern. That doesn't make any sense. But every time, right, I don't even need it to go one at a time. I don't care if it goes one at a time. If you get a wave distribution, this is counterintuitive, because we know that electrons are particles, because we see a spark. A spark is not a wave. A spark is particles. So we know electrons are particles. So you take this spark and you, in a vacuum tube, right? This is in a vacuum tube. In a vacuum tube, you take the spark. Oh my God. You take the spark, and this is positive. Oh, you can't see. This is positive, and this is negative. So it's attracted. And this beam, you have a beam of electrons. The spark, a continuous spark, you send it to the positive plate through two slits, and you get this wave distribution. How is that possible? We know that sparks are particles. They look like they don't look like waves. So how do you get a wave distribution? The only
Wait,
explanation is
sparks don't look like waves?
sparks are not waves. Sparks are particles. Where a
Sparks
spark is
are
not a
particles.
wave. When you touch a doorknob in the winter and you see the spark, that's not a wave. That's obviously particles. Those are electrons that are.
No, but those things they wave.
Wait, what?
The spark waves, I think.
No, a spark does not
Are
wave.
you sure?
What do you? A spark is a spark. It's not a wave. It's obviously particles. What do you mean? It doesn't behave like a wave. There's no propagation of energy in a spark. A
Who
spark
says?
jumps. A spark jumps from you to the doorknob. A spark is the motion of tiny particles that have gathered in your body for some reason as you were walking on the carpet in the cold, dry
Yeah, but
winter.
it produces an electromagnetic wave. I mean, ChatGPT is confirming that it does.
No. No.
Yes, it does.
No. Electrons are not electromagnetic waves. No. Electrons are particles. They're not electromagnetic waves. Electron motion, electron acceleration,
Yeah, but there's motion of electrons in a spark.
yes, it creates an
And
electromagnetic wave.
ions.
It creates an electromagnetic wave.
Okay.
But electrons are not waves. Electrons are particles. And this is now a cathode ray tube. It's vacuum, and you just heat up the filament, and it's negatively charged, and this plate is positively charged, and there is a vacuum, and there is two slits here that is neutral, and this beam goes through these two slits, and you create a wave pattern. How does that work? There's no explanation to this behavior. This cannot be understood unless you say that this beam, when I'm not observing it, if I'm observing it, it will just be two beams. But if I'm not observing this beam, if this beam is transparent, the more transparent the beam is, the more it converts into a wave. And this wave goes through these two slits, and it becomes two waves. And then they interfere with each other, and you get all these patterns. But you know that it's particles. So each one of these are particles hitting your detectors. Well, so you need to do them one at a time. So let's say you fire it very slowly, so you see each time a single detection. But you never see two detections at once, or three detections at once.
Yeah.
It's always one particle. How is that possible? How is that possible? Well, the question is, I mean, if you see two detections at once, the question is, are you able to send out one electron at a time? I really need to go to sleep. You
Yes,
send out.
you are able to do that technically.
How do you know?
Yeah, I mean, there are devices that do that.
Okay. So you send out one electron, it goes through two slits, and then hits a particle detector as one particle. How does it do that? How does it not become multiple? How does this spot know to communicate with this spot? So you could say that they're communicating because it's a short distance. But how? How do they communicate? I mean, you need intelligence for this. That doesn't
Yeah,
make
it's
any
the
sense.
strange part. I need to think about that.
No. There's nothing to think about.
Yes, there is.
No. This is just entanglement. This is just the collapse. This is just the collapse of the function, of the wave. This is the nature of the beast.
It's a strange nature.
No, there's nothing strange. It's like saying that everything. There's nothing strange. That is that is nature. That is just nature. There's nothing. I used to speak like you probably like a month ago, but now I just accept it. It's just the nature. I understand that it's not me. It looks like weird mechanics because we believe the mechanics to be propagation of energy through the ether at the speed of light. But apparently, it's possible to have instant communication. It's an instant draw of the luck, draw of a dice, of a die. A die is cast in real time. Someone is like God, for every particle, God is casting a die and is selecting the probability, or it's selecting, it's deciding where will the wave materialize or collapse into a particle. For every,
I don't know about that.
I mean, that's what it looks like.
It needs to
obviously-
be different. Because, like, you can imagine this in other ways.
How?
You can, like, let's say you have a wave propagating. So you have so you have like a field, and the field is moving. So how do you get the entire field to? Okay, so basically every type of, like, let's say it's like quantum field theory. So it's just a field of electrons that is moving.
No, I wouldn't say it's a field of electrons. It's a field of ether, and the electron is an electron wave in the
Okay.
ether, in the quantum. You could say I would say it's an electron wave in the quantum field, not an electron in the quantum field. Electron field. I don't see the reason for an electron field. I cannot accept two fields overlapping. So it's one field. It can wave electrons, it can wave photons, it can wave quarks, and so on.
Okay, unless, of course, there is a longitudinal wave within that
A
wave.
longitudinal wave? I don't know what the nature of the wave of an electron is. I don't know. I didn't think about that.
Okay, imagine that in your experiment, the wave, it's the electron. In your experiment of the photon wave, it's both electrons at the same time.
Let me show you.
More
Let
or
me
less.
show you. Let me show you a type of a wave that I would say an electron is. So here is a wave gun. Let's see a wave gun. No. This one.
According to legend, a really good blast of air should be able to bring down a house of straw. Let's see how it goes with an explosively generated vortex ring.
Here goes. This is the gas.
It's the first time it's ever been fired, and with 150 litres of one of the world's most explosive gas mixes in there, I'm not even sure that this is really a safe place to stand.
Seems about right. I'm gonna need these, I reckon.
Okay. 3, 2, 1. Oh, yes! Call me hopeful, but there was definitely something there. But was it a vortex ring? Filmed
You
at
see?
13
That's an
frames per
electron.
second, there is no doubt. But the ring you can see is not a smoke ring. It's formed by the pressure drop within the vortex.
So in the ether, you can have all types of waves that are not necessarily like normal water waves. You can have all sorts of waves interacting with themselves through a Fourier. It's not even a Fourier. You could say it's a Fourier interaction, but you could have all sorts of waves that end up even looking like they could look like a particle. They might, but that would not explain the two-slit experiment. So an electron cannot be a wave that looks like a particle, because then it would not. I don't think it would be able to go through two slits and still remain an electron. I don't know, but. Anyway, that's like one of the ideas that I'm having. There's all sorts of wavings. There's many types of wavings that you can create. By the way, they create to create rain. You can use these to create rain. Did you know that?
Like that?
Yeah, if you just point it at the clouds, you can cause the cloud to start raining. Anyway, yeah, these are big vortex cannons, and I saw somebody aiming it at a cloud. Let's aim it at a cloud. Effect no. Anyway, let's wait. Aim it at the sky. Yeah, I don't see it. I don't know why we can't see it. But you should be able to. I mean, a cloud is very low, and if you have a low rainy cloud, yeah, you should be able to shock it and to cause it to
Yeah, makes
collapse.
sense.
And yeah, I mean, I don't know if they're successful at it, but I saw somebody firing at the
Just
sky.
to know if it would cause like that much rain, like you could cause a chain reaction maybe.
Look, yeah, I mean, it's probably a chain reaction. You probably, you start something. Anyway, so
Yeah,
so
we should think about this.
Look, I thought about it, and because if the ether, if you assume ether, if your theory of gravity is ether, then you cannot have particles in this universe. Everything must be a wave. If everything is a wave, now then this makes sense. It's a wave, and only when you interact, it shows up. It shows up as a particle. It shows up as a point energy. But how does it know to show up at exactly one place? So this gave me the intuition of entanglement. So this means this. No, actually, no. I don't know. Maybe it was just thinking about Planck's equation. Oh yeah, I think maybe it was Planck. So maybe putting Planck together with just Maxwell's the way I imagine Maxwell waves. So if I'm using the minimal, if I just assume, and this you assume just because Planck said that energy there's that light can have. There's a minimal energy that light can have. So if you take Planck seriously, that there's a minimal energy that light can have, then you can only introduce that energy into the system. There's a minimal. You cannot introduce less than this energy. So given a frequency, F naught, you can only have E naught introduced into a system. So this is E naught, given that this motion is done at F naught. But this means that this is what they call a photon. That means when you finally interact with it, then only one of them can interact. I mean, it's not even this. It's conservation of energy. It's what. So you know, but you could say that this is E naught over 2, right? That's what you should. You could have said it's E naught over 2, and this is E naught over 2. But because of Planck, this would be a violation of Planck, and you cannot violate Planck. And the question is, why is Planck right? We need to know why Planck is right. But if Planck is right,
Yeah, he's right.
then you must get entanglement. If Planck is right, then only one electron in the universe should be affected by E naught. You cannot distribute E naught. I would say that you would lose the energy. No, you wouldn't. You still can't. But no. So why is there a minimal? So I would say the minimal energy has to do with the nature of ether. That H tells us the very nature of ether. This is the nature of ether. This is the minimalist energy that the ether can relay. Anyway, I'm going to go to sleep because I have to wake up early.
Yeah, same. Well, see you
Okay,
tomorrow.
man. We need. Are you going to be here tomorrow?
Yeah, probably.
Okay, I'll text you when I'm ready and we'll continue.
Nice. See you.
All right. Thank you. Good night. Wait,
Thanks,
there's
too.
messages from Dream and from Nicholas. The detector is also made out of electrons and protons. The Planck. He always talks about the Planck field. You know, once I thought he's a troll, but he's not.
No,
He
he's
really means it. Okay. Anyway, good night. See you tomorrow.
Good night.
Bye.